let's see an example of applying Ford-Fulkerson's algorithm in order to find the maximum flow of this example network. So we're given the capacity of each edge already, and the first step of Ford-Fulkerson's algorithm is to assign a flow value of 0 to every edge. Now we'll repeatedly find an augmenting path using, let's say, depth first search, and then increase the capacity along that augmenting path appropriately, increasing by the residual capacity for forward edges, decreasing by the residual capacity for back edges. So let's suppose, since there are many augmenting paths, let's suppose that the first augmenting path that we find goes from S to U, from U to W, and from W to T. Now the residual capacity of this path is 1 because the residual capacity of this edge is 5, of this one is 1, and of this is 7. So the smallest value is 1. We'll increase by 1 along each of these forward edges. And this is how we get the resulting flow network on the top left. So the new flow value of this is 1. Now there are still augmenting paths left to find, so let's suppose that our modified depth first search finds the following augmented path along this forward edge, this back edge, this forward edge, and this forward edge. Now the residual capacity of this entire path is 1 because the residual capacity of this edge is 3, of this back edge is 1, of this forward edge is 2, and of this forward edge is 5. So the smallest value is 1. We'll increase by that residual capacity along those 3 forward edges that we have, and decrease by the residual capacity 1 along this back edge. And this is how we come up with the resulting flow network below. We've increased the flow by 1 now. Okay, now in this network, let's suppose the next augmenting path we find via depth first search goes from S to V, from V to W, and W to T. These are all forward edges. The residual capacity of this edge is 6, of this edge is 1, and of this edge is also 6. This is how much additional flow we could send through. But the smallest value is 1. So the residual capacity of the entire path is 1. We can increase the flow along each of those edges by exactly 1, and we're left with the following graph. So we've increased the flow of our network by 1. So the flow of this network at this point is 3. And there are still augmenting paths along which we can increase the flow. So let's suppose now the depth first search, next time we use this to find an augmenting path, finds the following paths. From S to V along a forward edge, W to V along a back edge, and V to T along a forward edge. The residual capacity of this forward edge is 2, of this back edge is 1, and of this forward edge is 3. The smallest value is 1, so we can increase by 1 along those forward edges, and we decrease by 1 along this back edge. So we've increased the flow of this network by 1. Okay, now assume that the next path that we find with depth first search, the next augmenting path we find is from S to V, and then from V to T. The residual capacity of this path is 2, because the residual capacity of this edge is 5, and of this edge is 2, and 2 is the smallest. So we increase by exactly 2 the flow along each of those edges. And this is how we get the resulting graph in the top left. Alright, now from this graph, we still have augmenting paths left to find. There are quite a lot using this depth first search. So let's say we find a path from S to V, from W to Z, and then from Z to T. And these are all forward edges. The residual capacity of this path is 1 because this is the smallest residual capacity of each edge. Of this edge, its residual capacity of 1 is 1, of this one it's 9, and of this one it's 4. So we can increase by that smallest residual capacity, which is 1. And this is how we get the resulting graph below, increasing by 1 each edge along that along that augmenting path that we found. Now suppose that the modified depth first search we use to find an augmenting path finds the following path from S to V, this forward edge from V to W, and this forward edge from W to T. Now the residual capacity of this edge is 3, of this edge is 1, and of this edge is 5. Smallest value is 1, that's the residual capacity of the entire path, we increase by exactly that value the flow value of each of these forward edges to get the resulting graph. So now the new flow of this graph, of this network, is 8. Alright, now in this, suppose we find another augmenting path from S to U, from U to W, and from W to T. And along this we can increase the flow by exactly 1. This edge is the maximum, is the smallest residual capacity, which is our bottleneck. We can't send any more than 1 through this. So our new total here is 2, here's 1, and here's 4. Okay, now what else can we find? Notice that we can't find anything from V. We can't set anything else. So while we can get to S, get from S to V following an augmenting path, from here we're stuck because we can't send anything more from this edge from V to T or from V to W. We can't send anything from S to W either because this edge is maxed out. So the only augmenting path that we have, which remains, starts at S and goes from S to U. We can't go from U to W anymore now that we've maxed this out. So we have to go from S to U, from U to Z, and then from here we can already get to the sink T. The residual capacity of this path is 1, so we can increase the residual capacity of this edge is 3, of this edge is 1, and of this edge is 3. Smallest value is 1. So we can increase the flow along this path by exactly 1. So both of those steps are shown in the next graph. And this really is the maximum flow now. So we found that the maximum flow of this network is 10. There is no augmenting path, and we can prove this by finding a cut of minimum capacity. So what vertices could we reach along an augmenting path? From vertex S, we could reach vertex U. We could reach vertex V, but those are the only things that we could reach along an augmenting path. From V we can't get anywhere else because these edges are maxed out. From S we can't follow this edge because it's maxed out, and from U, again, these edges are maxed out. So this defines a cut X of minimum capacity. This cut has capacity 10, and it has flow 10, which is the flow of our network, and this is the maximum flow we could get. So this cut is really describing what the bottleneck part of this network is, why we can't send any more flow through it. Now, you might have noticed that with Ford-Fulkerson's algorithm, we might get really unlucky in the sense that we find an augmenting path, but we can't increase the flow along that augmenting path by very much. If we're unfortunate, then if, let's say F star, let's say this is the maximum flow of our network, we might have to find an augmenting path this many times. If that augmenting path that we find only has residual capacity of 1, then we only ever increase the flow of our network by 1 each time. And in that case, we'd have to find an augmenting path this many times. And finding an augmenting path is linear time, n plus m, just using that modified depth first search. So the running time of Ford-Fulkerson's algorithm is this. And this is unfortunate because we actually don't know what the maximum flow is yet. This is part of our algorithm, what we want to find. But this gives an example of when the flow of a network would only ever be increased by 1. Say we have this kind of bottleneck edge, which has capacity 1. The first time we run Ford-Fulkerson's algorithm with depth first search, we may find this edge from S to U, U to V, and V to T. Its residual capacity is 1, so we only increase it by 1. Then the next time we run this algorithm, we find an augmenting path from S to V. We use this back edge from V to U, and then forward edge from U to T. This edge has residual capacity, this back edge has residual capacity of 1, so we can only increase it by 1 again. So each time, if we repeatedly find those paths, we can increase by 1. Even though the maximum flow here is 50, Ford-Fulkerson's algorithm would have, in that case, up to 100 iterations, only ever increasing by 1 each time. It would be much better if we could immediately find this path to increase the flow along, and this path to increase the flow along, rather than using this bottleneck edge. And this is exactly what Edmonds and Karp try to do. This is a variation of the Ford-Fulkerson algorithm, where instead of using depth-first search to find an augmenting path, Edmonds-Karp algorithm uses breadth-first search. So they show, and the proof is in your book, that if we carefully select which augmenting path to take at every iteration, namely the one with the fewest edges among all possible augmenting paths, then we can implement Ford-Fulkerson's algorithm in m squared total time.